Hello, everybody. My name is Masoud Olia, and I'm a professor in the School of Engineering at Wentworth University. And I have another problem for you today related to the topic of kinematics of rigid bodies. In particular, here we have this link ABD, as you could see here, connected to a hydraulic cylinder, and as you could see, point B, given it has a speed and an acceleration at this instant pointing up vertically. So these are given here: velocity of B and acceleration of B. So this is basically a combination of velocity and acceleration problem. And what we are trying to find, we want to find acceleration of point E, this point at this instant, the end of this rod ABE. Okay, now you have to understand, guys, that, and you've probably seen this in the other videos that I've had, that when you do acceleration analysis, the first thing you need to determine is all the angular velocity of all the bodies involved. So in this case, we need to figure out what is the angular speed of the ABE. Okay, and that could be done very easily because we have velocity of point B, as you could see, it's pointing up at 4 feet per second. And we know EA, which is within this cylinder here, has no choice, but like a piston has to move left or right. So we could actually use IC. So first, we try to find omega of this link A. I'll just call it AE, or that's ABE, basically. So the way we do that is using, the quickest way is using IC method. Remember, IC method, I have a bunch of videos, you can go and look at them. Just do a search on velocity analysis using instantaneous center. So IC stands for instantaneous center. So basically in IC method, you need velocity of 2 points, at least the direction of them. So if we draw, we could even do it right here. Look, velocity of B is up and is equal to 4 feet per second. Then in that case, A has no choice but to move to the left, right? So you know that if you have velocity of 2 points on the body, what do you do to find the instantaneous center? You draw perpendicular lines to these two velocities, to velocity of B at point B and to velocity of A at point A, right? The point of intersection, I'm just going to call it C for center, and that becomes the instantaneous center. Let me redraw this here for you. So basically, this is velocity of B, right? And this is velocity of A. And as I said, we draw perpendicular lines to these two velocities, right? And we call that point C. Again, you could visualize as if this is like a triangular plate now. Kind of you extend the body. And the body, as you could see with these velocities, the way they're acting, clearly is rotating. Which way? Rotating clockwise. So I'm going to call this omega of AE. I refer to the endpoints. Okay. So how do we find omega of AE? Very easily. First of all, we could figure out these distances here. We basically need the distance from B to C. Now, knowing that this angle is 30 degrees here, this angle, and knowing that the length of the segment of AB is 2 feet, right? So this hypotenuse from A to B is 2 feet. So therefore, BC simply becomes 2 cosine 30. And 2 cosine 30, I have it right here, is 1.732 feet. So instantaneous center says, well, okay, you want to find velocity of a point, so C becomes the center of rotation at that instant, all right? So you connect from the center of rotation to the point, so that becomes the radius CB or BC times omega of the bar, which I will call it omega AE. So velocity of B is given to be 4 feet per second. At that instant, I just calculated CB from the geometry for you, 1.732, and then you can go ahead and find omega AE. So, and that's the key in solving this problem. You need omega AE, which happens to be 2.309. So what I'm trying to say, guys, is that don't try to do any acceleration analysis before you have calculated all your omegas. So now that you have omega AE, basically forget about velocity analysis. In other words, some people get attached to this point C, the instantaneous center. That's the instantaneous center of zero velocity, guys. It has no significance for acceleration. So if I were you, I would just erase this, right? Yeah, we did the analysis here to find omega AE, which we need, and we'll use it in a few minutes. So now, how do we approach acceleration? So I'm going to call this acceleration analysis now. So now we're moving to doing acceleration analysis. Okay. So how do we do this? We need to find first, in order to find acceleration of E, we need to actually use the information regarding to acceleration of B, and the fact that we know A has no choice but to move horizontally to the left or right. And first find alpha of this bar AE. Once you find alpha AE, then you can go ahead, having alpha AE and omega of AE, which I've already calculated for you, then you should be able to solve for acceleration of E. So first we have to find that. So how do we do that? Let's see, we have to write the relative motion equation between point A and B, because we have the information regarding acceleration of B. So for example, you could say acceleration of A is equal to, and it doesn't matter, you could say start with acceleration of B or A. I'm going to translate with B, and I'm going to rotate about B. Remember from other videos that the first term is the translation part, the second term is the rotation part. And then keep in mind that this part consists of two components, AN and AT. This acceleration of A relative to B means what? Means find acceleration of A as if B is fixed. That's what it means. And we're not saying B is fixed, but that's the way we have to approach it. Okay, so let me show you what's going to happen. So if this is our bar, right, and this is point B, and this is point A, right? If we make B fixed now, imagine if B is fixed like that. And we already know that this bar is what? Rotating clockwise, right? With an omega that we've already calculated. And the alpha, we have to make an assumption. What do we assume? That alpha AE is also in the same direction as omega. Basically, we're saying it's accelerating. So this part, there are two components. You want to find the acceleration of A as if what? B is fixed. So there are two components of this acceleration. Let me go back to red. So there is a normal component, and there is a tangential component in the direction of assumed alpha. See, alpha AE is assumed to be clockwise, right? So what are these components, by the way? How do we calculate them? AN, I write it down here. AN is R omega squared, right? R is what? R is the distance between A and B. That's 2 feet, right? Times omega. Omega we have. You see, that's why you need to calculate omega from the beginning. So what is 2 times 2.309? I believe it's 10.66 feet per second squared. So that's a normal component. I'll put it here. And there's a tangential component, which I'll move down a little bit and say, okay, the tangential component is R alpha. R is what again? 2, right? The distance between A and B. Alpha is alpha of this link, AE, or AB, or ABE. Just one bar, right? All right. So and look at the direction based on the angle that we have here, this 30 degrees, you will put that in here. I mean, you could do it based on the IJK business, you know, do it vectorially, but this is what I call a scalar approach. So look, acceleration of A, what do we know about acceleration of A? Well, all we know is that we're assuming that A is, well, it's moving horizontally, but we're gonna assume that it's moving to the left, just like velocity. So in other words, we're saying A is accelerating. Well, we'll find out. If we get positive, fine, the direction is okay. If we get negative, we have to change the direction. Okay, what's the acceleration of B? That's given, guys. Look, 1.5, remember, feet per second squared, it's up. And look at the two components that we were talking about. AN, this is the rotation part of the motion, the acceleration of A relative to B, right? Which I showed you here. Find the acceleration of A as if B is fixed, right? So 10.66, like that. And the tangential one, which is the 2 alpha AE, like this. And remember now, we do have both angles, but this one is perpendicular, so this angle must be 60 degrees. So the key is getting what? Alpha AE. So it looks like if we actually just equate the vertical components of both sides, so if we just concentrate and zoom on vertical component, notice that there is no vertical component here. So we have 0 on left-hand side, we have 1.5 up, a 10.66 sine 30 up, and a negative 2 alpha AE sine 60. So if you go ahead and solve for the only unknown here, which is alpha AE, what are we going to get for alpha AE? Alpha AE comes out to be 3.945 and positive, guys. See, this was an assumption that we made. The fact that we get a positive implies that we were right. So in fact, this bar is accelerating and its direction is, as indicated, clockwise, just like the way it's physically rotating. Okay? So we achieved our goal of finding acceleration of angular acceleration of rod AE. Let's go up and take a look at this again, guys. Now we want to find acceleration of E. What do we have? We have omega of AE and alpha of AE. So, and we have acceleration of B. So why don't we just use B as a reference again and try to find acceleration of E, writing the relative motion equation, right? So let me move this up. This did get stuck again, looks like. All right. So look, guys, by the way, I could come and find acceleration of A, but I don't need that. So I'm going to say now acceleration of E is acceleration of B plus acceleration of E relative to B, meaning that, again, we translate with B, we rotate about B. Look, guys, we already have made B fixed here. So we could actually use the same picture, right? So in fact, this part of the motion again is what? Consists of the AN and AT. AN is R omega squared and AT is what? R alpha. But R is what this time? R is the distance between what? B and E. This acceleration of E relative to B means what? Means find acceleration of E as if B is fixed, like what I had here. I already have B fixed. Might as well just use the same picture. So, and the difference is now that we do have both omega and alpha. We calculated alpha. So R is what? The distance between A and B, E and B. So that's actually, if you go back up, I believe it's what, 1 foot, right here, right? So this distance is 1, right? So 1 times omega, this is omega of AE clearly, so that's 2.309 squared. I believe this becomes 5.33, right? And this R alpha also is 1. Alpha, remember, we calculated 3.945. So it's 3.945 feet per second squared. Unit, by the way, feet per second squared. But what about the direction, guys? Look, it's acceleration of E relative to B, which has two components, right? This is the normal component, and this is the tangential. Tangential is in the direction of alpha. Remember, alpha is rotating which way? Clockwise, right? Like that. So the tangential would be like that. So I'm going to move down here again, and I'm going to plug in. Let's go back to black. So acceleration of E is, now acceleration of B, remember that's 1.5, that's given. We had it here also. Two components of acceleration of E relative to B are AN. AN came out to be 5.33, like that, at 30 degrees. And acceleration, the tangential component is R alpha, which is 3.945. And again, based on the angle that we have, this must be 60 degrees. So now go ahead, guys. Everything is known now. Look at the X component of acceleration of E. Call this X component of acceleration. What do we have? 0 from this guy, 5.33, cosine 30, 3.945, cosine 60. If you calculate this, looks like the X component becomes 6.59 feet per second squared. And similarly, if you try to add the Y components, you have a 1.5 here. You have a negative 5.33, so it's pointing down, right? Like that. Sine 30, right? And a positive 3.945 sine 60, positive, right? This comes out to be overall 2.25 feet per second squared. By the way, units are feet per second squared. Okay. Now that you have the X component and Y component, then you can find the magnitude of acceleration, right? 6.59 positive, right? This one, and 2.25 roughly. So acceleration of E at this instant would be like that. Square root of 6.59 squared plus 2.25 squared. That comes out to be about 6.96. If you like to know the exact direction, you can figure out this angle, call it, I don't know, phi, right? Phi is inverse tan of 2.25 over 6.59, which is almost 19 degrees, 18.8 degrees. Okay, so if we come up here, acceleration of E at this instant, it will look like what we just got, like that. That almost 19 degrees, like that. All right, guys, I hope you like this video. As always, I would appreciate it if you, like my video and subscribe. I'm always coming up with new videos. And have a good day, and I'll see you soon. I'm going to stop this. Thank you.